So last week, our content was relativity, which is one of the sort of great 20th century revolutions in physics. This week, the remainder of the course is quantum mechanics, which is the other sort of great revolution, physics revolution of the 20th century. So this class, next class, and Tuesday's class, we're going to be talking about what's called quantum mechanics, a type of mechanics that's different from classical mechanics that applies to atoms, molecules, subatomic particles. So today's class is going to focus on one aspect of quantum mechanics, and it's light in quantum mechanics, and it's going to introduce photons as particles of light. So the specific content for today is I'm going to talk a little bit about the beginning of the 20th century collapse of classical physics. So classical physics is the physics prior to the 20th century. It's the physics of classical mechanics, of electricity, of magnetism, of, I've forgotten the other thing, it's of heat. So that's classical physics. And we'll talk about how that collapsed, how that broke down. We're going to talk about two phenomena that led to the breakdown of classical physics, and they're listed here. So the first phenomenon is called black body radiation. So I want to tell you what black body radiation is, and then we're going to see how classical physics couldn't explain black body radiation, but some ideas introduced by a scientist called Max Planck, who's one of sort of the fathers of quantum physics, were able to solve the problem of black body radiation. The second effect I want to talk about is called the photoelectric effect. This is also a phenomenon that could not be explained classically. It required quantum physics to explain it. And we'll talk about the ideas that were introduced by Einstein to explain the photoelectric effect. And through black body radiation, through photoelectric effect, we'll uncover this world, this quantum world, this microscopic world of particles of light that we call photons, quantum of light that we call photons. Okay, so this is a classical electromagnetic wave, such as light. So this is a beginning of the 20th century picture of light. And that classical picture of light is that light is built out of electric and magnetic fields. It's built out of vibrating, oscillating electric and magnetic fields that are self-sustaining. They sustain themselves and they propagate through space. They carry energy and momentum. In the classical picture of light as an electromagnetic wave, the electric and magnetic fields in the light could take any value you like, any value whatsoever. There's no restriction in principle on the values of the electric and magnetic fields in an electromagnetic wave. In addition, in the classical picture of light, the energy that's carried by the light, the momentum that's carried by the light, those could take any values whatsoever. So the energy and momentum that's transported by light could be any value whatsoever in the classical picture of light. These are the two things that really broke down and led us to introduce photons, because we'll discover that at the microscopic level, at the level of atoms and molecules and subatomic particles, then light can't carry just arbitrary amounts of energy and momentum. Light's electric fields can't be arbitrary values. These quantities come in certain sizes, certain packets, certain quanta. Okay, so what happened specifically was that up to the beginning of the 20th century, physics knowledge was basically that of mechanics. You talked about that in 211. Electricity and magnetism, we talked about that in 213. And also heat, which we talked about a little bit. So that's pre-20th century physics, and that collapsed. That physics was not able to explain early discoveries in the early 20th century related to space and time, which is what we did last week, and light and matter, which we're doing this week and next week. So classical physics could not handle these topics and needed the introduction of relativity, needed the introduction of quantum mechanics. As I mentioned, Max Planck, Albert Einstein, and others were responsible for developing a new sort of mechanics to replace classical mechanics that we call quantum mechanics to describe matter at the microscopic level, to be able to describe atoms and molecules and subatomic particles correctly. So that's why quantum mechanics was introduced to describe the motion of atoms and molecules at that very small scale. We call all this modern physics, and I'm thinking that we call it modern physics because at the beginning of the 20th century, that's when modern art started to emerge, and modern literature, and modern architecture, and so we came up with modern physics. Modern physics, to me, means relativity, means quantum mechanics. It means those foundations, those parts of physics. It's the post-electricity, magnetism, mechanics, and heat physics. Okay, I want to show you a demonstration of black body radiation. Then we're going to talk about black body radiation. To show you the demonstration, we're going to look at this lamp. And this lamp here is an example of black body radiation. And actually, we're surrounded by examples of black body radiation, and we're examples of black body radiation. So we're going to look at it for the case of the lamp. I'm going to set the mood, of course. And I'm going to switch on the lamp. And what I'm going to do with the lamp is I'm going to gradually turn up the current that's flowing through the lamp. Now, that electrical current that's flowing through the lamp is flowing through a tiny filament, a tiny wire, thin wire. Because it's a tiny filament, thin wire, it's going to get hot. And as I turn up the current, it's going to get hotter. And as I turn it more, it's going to get hotter and hotter. And what we're going to see is it's going to glow. That's how incandescent lamps work. They glow because their filaments are getting really hot. And we're going to look at the glow of this lamp. Now, the thing about this lamp is that I can increase the current, decrease the current. We can see how the glow, which is black body radiation, changes as I increase or decrease the current. So that's what we're going to watch. So right now there's no current. And so I'm going to start turning the current up. There's a little current now. I can't actually see anything. I'm sure you can't. Now I've got a lowish current, and I hope you can see it glowing this sort of red color. And so that light, that radiation, so I'm calling the light the radiation, this light is black body radiation, that light is kind of a red colored light. Now, if I increase the current some more, two things have happened. One, I would say that this is more of an orange-colored light now, so that the color has changed somewhat. And also, it's quite a bit brighter now. It's a lot brighter now. Now, I'm going to turn it up a bit more. So now, I would say that it's more of a yellow-colored light. Again, the color has changed. The wavelength, the frequency of light has changed. And also, it's a lot brighter still than it originally was. And I could keep on doing this, right? I'm going up now. I barely can look at it now. I'm blind. It's bright, kind of white yellow, and it is really bright now. And we could go on and go on. Now, if I could do it, I cannot do it because it will break. If I could really turn up the current, it would go through white to blue. It would actually start to glow blue, but the lamp would break by then. But anyway, I'm going to turn it back down. So I'm just turning the current down. You see it get dimmer and dimmer. That's one effect. You see its color changing. It's more of a yellow now. It's going towards an orange now, getting really kind of dim, going towards the red end of the spectrum now, and ultimately vanishes on us. And that's black body radiation. So the story I'm going to tell you now is, firstly, why black body radiation, why the features of black body radiation, so the color of the black body radiation and the intensity of the black body radiation, why that broke classical physics, or where that broke classical physics. And then I'm going to tell you the story of Max Planck, famous scientist who came up with a hypothesis, an idea, a notion of how to fix up the theory of black body radiation and reproduce the features, the color of the light, the intensity of the light of black body radiation. So the next few slides are that story, the breakdown of classical physics, the hypothesis of Max Planck to explain black body radiation. Okay. Before I do that, though, I forgot this. I want to tell you about the sun, because the sun is a classic example of black body radiation. And a sun is a very important example of black body radiation. And the sun, like the filament in the lamp, both of them emit black body radiation. And I wanted to just tell you, sort of conceptually, how they emit black body radiation. How does the sun emit it? How does the filament emit it? Well, the sun, as you know, is some giant ball, massive ball of hydrogen. And it's a giant, extremely hot ball of hydrogen gas. And you can think of it as the sun is a giant hot sea of fast-moving, randomly moving electrons, of fast-moving, randomly moving charged electrons. Now, we know from our work on electromagnetism that charges, randomly moving charges that are accelerating around, will emit electromagnetic radiation. And that's the source of the radiation from the sun. That's the source of the radiation from the lamp. And that's the source of black body radiation. It's due to the thermal motion, the fast, random thermal motion of the electrons in the sun, or the electrons in the incandescent lamp. So that's where the black body radiation comes from. It's not like a mystery. We don't understand it. We know where it's come from. It's coming from the electrons and an electromagnetic theory producing light. This slide here shows you, we talked about the color of the light from the lamp and how the color changed from red through orange, through yellow, through white. This is the spectrum of solar radiation. This is the spectrum of black body radiation, the spectrum of light from the sun. So on this graph here, the horizontal axis is wavelength. On the far left of this graph, over here, these wavelengths, so 250 nanometers, that's shorter than visible light. That's ultraviolet light. So that's the light that will give you sunburn, suntan. That's over here. In this region here, this is from something like 400 to 700 nanometers. This is that region of visible light that we can see with our eyes. So this is the red through violet that we observe in our daily lives. And then to the right of that, so from 700 up to several thousand nanometers, this is what we call infrared. So this is the infrared region. You can't see that with your eyes, but you can measure this with a thermometer, for example. Anyway, so that's that axis. And then the vertical axis is a quantity that we met when we talked about electromagnetic waves. We talked about intensity. Intensity is the amount, reflects the amount of energy that the electromagnetic waves carries. Specifically, it's the energy, joules, per second, so per unit time, per unit area, per square meter. That's the intensity here. And so, you know, downstairs here is 0 intensity, and upstairs here is a larger intensity. And I'm measuring it here in watts per square meter. The black curve, no, let's not start at the black curve. Let's start at the yellow graph here. What's that? That's the solar measured. That's the measured solar radiation spectrum at the top of the atmosphere. So if we went on a field trip, we would go up to the top of the atmosphere and we measure the solar radiation spectrum with some solar radiation spectrum measuring device. That's what we get for this yellow curve here. You see that it's peaked around visible light. Maybe we evolved to see that, perhaps. Of course, I know nothing about evolution, but maybe we did. So it's peaked around the visible region, and it falls off in the ultraviolet, and it falls off in the infrared. The red curve, what's that? Supposing we didn't go on the field trip. We just stayed here and we went outside and measured the intensity of sunlight at sort of approximately sea level, beneath the atmosphere. That's what we would see here, this red curve. It's an interesting curve, especially today with climate change. It's an interesting curve because lots of, it's lower in intensity, right, overall, but it's got lots of holes cut in it. It's got lots of holes cut in it because of what's in the atmosphere, because of ozone cuts a hole in it at the, in the ultraviolet region. Water vapor, you know, water vapor's in the air. There's clouds of water vapor. The water vapor cuts a hole in the spectrum at various places. And famously, carbon dioxide also cuts holes in this spectrum. You see that over here. Anyway, that's the red. The black line is theory, and it represents the spectrum of sunlight at the top of the atmosphere pretty well, I would say. This is Planck's theory of black body radiation. And so this is our goal, to understand this theoretical prediction here. You see it has a peak wavelength in the visible. It falls off at short wavelengths in the ultraviolet. It falls off at long wavelengths in the infrared. And it reproduces the solar radiation spectrum, because the solar radiation spectrum is approximately black body radiation. Okay. So that's the sun, but with lamps like this, scientists explored and examined and measured black body radiation, and they came to a number of conclusions, a number of empirical facts, a number of observations about black body radiation. One of them is about what we talked about, the color of the black body radiation, and the other one is about the intensity of the black body radiation, and specifically how the color changes with, I changed the current, but really I was changing the temperature of the filament, and how the intensity changes with the temperature. I didn't directly change the temperature, I changed the current. But there's two conclusions two laws that are empirical laws, sort of observational laws that describe black body radiation. So one's called the Wine law. That has to do with, it's not W-I-N-E, it has to do with the color of the light, the frequency of the light, or the wavelength of the light. And the other one is Stefan Boltzmann law. That has to do with the intensity of the light, the amount of energy that the light carries. And both of the laws have to do with how the color of the light, the intensity of the light, depends on the temperature of the black body. And so on this plot is, again, horizontally is wavelength. So in this particular case, we've got wavelengths that in units of micrometers. So a micrometer is 1,000 nanometers. So this is a range of 1,000 nanometers. The visible light is sort of around a half a micrometer, 500 nanometers. So this is the rainbow of visible light here in these vertical bars. And then over here is the intensity. And what's indicated on this plot are three different curves, the green one, the blue one, the brown one. They're the black body radiation at three different temperatures. So this is what is measured when you have a filament, say in this lamp, at three different temperatures, 2,000 Kelvin, 3,000 Kelvin, 4,000 Kelvin. So there's two key features on here, which are the two key features we saw with the incandescent lamp. Look at the lower temperature, and then compare it with the intermediate temperature. Compare it with the highest temperature. So just in your head, walk through from 2,000 to 3,000 to 4,000 Kelvin. The first obvious thing of the lower temperature is there's way less intensity. There's way less energy radiated in black body radiation. As you raise the temperatures, we go from 2,000 to 3,000 Kelvin, we dramatically increase the intensity of the light, the energy that's radiated in the black body radiation. As we go to 4,000 Kelvin, we further dramatically increase the amount of energy that's radiated by the light. We saw that with the lamp. I started to turn the current up, and to begin with, it just gradually, the intensity gradually went up, and then it started to really race away. It got really bright, hard to see the lamp. Okay. The other thing to observe on here is the wavelength of the light. And in particular, look at the peak wavelength of the light. So for the 200 Kelvin, that peak wavelength is about 1.5 micrometers, somewhere in here. As we turn up the temperature to 3,000 Kelvin, that peak wavelength is now a little below 1 micrometer. So that wavelength has got shorter. That means that frequency has got higher. And as we turn the temperature up further still, 4,000 Kelvin, that peak wavelength has moved to, maybe this is 0.7 micrometers. So it's moved to an even lower, a shorter wavelength. That's a higher frequency. So those are the two features that are evident on this graph. And these two laws describe that. So if you look at the, let's look at the Stefan Boltzmann law first. This is the one for the intensity. This is the most dramatic thing. Stefan Boltzmann law, this observational law, says that the intensity is proportional to the fourth power of the temperature. That's a super strong dependence on temperature. I don't know another law in physics, really, where you get such a dramatic dependence on a quantity. So this is a fourth power of temperature. That means if you double the temperature, right, if I can do this in my head, 2, doubling the temperature, intensity, how much does that go? It's 2 times 2, that's 4, times another 2, that's 8, times another 2, that's 16 times. You're going to get 16 times the intensity if you go from 2,000 Kelvin to 4,000 Kelvin. That's what you see here as you go from the green curve to the brown curve. 16 times more intensity of the light. That's what we saw with the lamp here. So turn the current up and turn the temperature up, got a lot brighter. Upstairs here, this is the other law. This is the law for the I think of this as sort of the color of the black body radiation law. This law says that if you take the temperature of the black body, that's the T, and you multiply it by the peak wavelength that's emitted, so that's the lambda max. So that would be the 1.5 microns for the 2000 Kelvin. It would be the 1 micron for the 3000 Kelvin. It would be the 0.7 microns for the 4000 Kelvin. If you multiply temperature and wavelength maximum, that's approximately equal to this constant here. What that's saying is that it's like a seesaw, right? If you increase the temperature, one end of the seesaw, you're going to decrease the value of the peak wavelength. You're going to shorten the wavelength. If you lower the temperature, that end of the seesaw, then you're going to stretch out the peak wavelength. You're going to make the peak wavelength longer. So the product of the two remains a constant, and that constant is this number here. You see this constant has the units of temperature, Kelvin, times meters for wavelength. So that's the color law. That's the kind of the brightness law. Okay, let me do this example. I'll do it on here, maybe. This one's quick. Okay, so it's an interesting question, though, because I said the sun was emits black body radiation. We talked about the lamp emitting black body radiation, but everything is emitting black body radiation. You're emitting black body radiation. Your skin is emitting black body radiation into this room right now. So is even mine is. In this problem, we're asked to calculate the peak wavelength of radiation that's emitted by each of us from our skin, the black body radiation. And we're going to do this knowing the temperature of our skin. I've put it here as 33 degrees Celsius. I think that's about right. I don't really know. We're going to use Wine law. So the Wine law says that the product of the temperature and the peak wavelength is equal to a constant. It's this seesaw, and the constant, if I remember it, was 0.0029 meters Kelvin. What that means there is that if we want to find the peak wavelength and we know the temperature, we can just rearrange this equation. All I got to do is take the constant, 0.0029 meters Kelvin, and divide it by the temperature. And that will give me the peak wavelength, what I'm calling lambda max here. So that's all I've got to do. I just got to fill in my number for the temperature. Now, one thing you got to do with this equation is to fill in the temperature in Kelvin. The reminder is here. The units are meters Kelvin. And so we don't fill in the 33 degrees Celsius. We add 273 to it to get, I added, what did I add to it? Yeah, 273 to it. My brain doesn't work up here. It doesn't work other places too. 273 plus 33 is 306. So I'm going to plug in the temperature in Kelvin. And then, of course, I've already calculated this because I would be too anxious if I didn't. It comes out to be 9,470 nanometers. So that's the peak wavelength of black body radiation that you're emitting and I'm emitting right now in this room. Now, we don't see each other glow because that's not in the visible region. That's in the infrared region. That's much longer than that's 10 times, more than 10 times longer than wavelength and visible light. But you are emitting radiation. One reason you have to eat is you're losing energy. And one reason, it's a small reason, is that you're radiating energy. You're radiating black body radiation. Okay, now I want to tell you about ultraviolet catastrophe. So the ultraviolet catastrophe is the physics name for the fact that this spectrum of black body radiation related to the intensity and the color could not be explained by classical theory. The classical theory you need, notice my slide has slipped off to the side for some unknown reason that we can never fix. But anyway, classical theory of black body radiation is really based on two things: mechanics, because you've got moving electrons that emit the black body radiation, electricity and magnetism to understand how they produce light, and also heat, the theory of heat. The theory of heat tells you how the motion of the electrons is related to the temperature. So those key ingredients of classical physics can be put together in a bundle and predict the radiation, the black body radiation that you would expect. And that's what's shown on this graph here. So this graph is, again, a graph horizontally of wavelength, vertically of intensity. So it's the same type of graph as I've been showing you up to now for the sun and for other things, whatever they were. There's two curves now here. One curve is the experimentally observed black body radiation spectrum. That's the blue curve here. So this is the familiar one that we've been looking at. Remember, it has some peak wavelength. At very low wavelengths, it falls off and vanishes to zero. And also at very long wavelengths, it falls off and vanishes to zero. The extra curve, this brown curve here, that's the classical theory of mechanics, electricity, magnetism, and heat bundled together to predict black body radiation. Now, let me say a couple of things about it. At long wavelengths, so this is in the, say in the infrared here. Those are the long wavelengths. The agreement is actually very good. So the classical theory, as you go to longer and longer wavelengths, works very well. On the other hand, at short wavelengths, so up here, this is much shorter wavelengths, maybe in this sort of ultraviolet and visible light region, the classical theory is disastrous. It just does not reproduce the data. In fact, let me just think why we call it a catastrophe. We're not just catastrophizing, or whatever that word is. With being dramatic, overly dramatic. Well, we are, but I am now, I guess. The reason we call it a catastrophe is that if you observe black body radiation at short wavelengths, you see vanishingly small energy radiated. So at short wavelengths, experimentally, there's vanishingly small energy radiated. In classical theory, at short wavelengths, there's actually infinite amount of energy radiated. So that's why we're dramatic, call it a catastrophe, because the experiment observes nothing at short wavelengths, and the theory predicts infinite at short wavelengths. So that's a pretty big disagreement to reconcile. Did I miss a slide somehow? Oh, yeah, I did. That's a relief. So the problem of the classical theory with the black body radiation was kind of fixed up, was solved in a way, by a hypothesis of this scientist Max Planck. So his hypothesis was that the electromagnetic radiation that's emitted in black body radiation, the energy of the electromagnetic radiation actually can't take any value. I said in classical physics the energy carried by electromagnetic radiation could take any value. His idea was that the energy carried by electromagnetic radiation can't take any value. And actually, it can only take certain discrete sizes or packets or what we call quanta. So it only comes in certain sizes, packets, or quanta. So that was an idea, but he backed that idea up with an equation for the energy, the size of these packets, the size of these quanta, in terms of the frequency of the electromagnetic radiation. And that's the equation that you see here. So his idea quantitatively was that the energy comes, the electromagnetic radiation comes in packets. And the size of a packet, so here's the energy in a single packet, is equal to the frequency, that's the F here, times a constant that's called Planck's constant. So the value of the constant, I wrote it down here, 6.6 times 10 to the minus 34 joules seconds, or 4.1 times 10 to the minus 15 eV seconds. It's a constant that has units of energy times seconds, which means that when you multiply a frequency in inverse seconds by this constant, it turns the inverse seconds, or the hertz, into an energy. So it is a constant that morphs a frequency into an energy. This equation is clearly saying that at low frequencies, the sizes of the packets are tiny. At high frequencies, the sizes of the packets get big. That's the feature of this equation. The size of the packet is not the same for all frequencies of electromagnetic radiation. The size of the packet really depends on the frequency of the radiation. And his idea was that the energy in electromagnetic radiation could only come in units of these packets. So it could be, you could have electromagnetic radiation at a certain frequency having one packet, or two packets, or three packets, or no packets. So this En is the allowed values of the energy at a particular frequency, where N is just an integer that's counting the number of packets of energy that you have at that frequency. I mean, that's, in a sense, a crazy idea. We know from classical physics we got light is an electromagnetic wave. Why would we suddenly say, oh, well, the energy can only come in packets? I mean, there's no basis in electromagnetic theory, classical electromagnetic theory, for this crazy idea. It solves the problem of black body radiation, though. That's the reason that it was introduced, to solve the problem of black body radiation. The problem of black body radiation isn't apparent at long wavelengths. At long wavelengths, which are low frequencies, the sizes of the packets are tiny. And so you don't even notice the packet size at long wavelengths. And so the classical theory, if you add this idea, hypothesis to it, remains the same at long wavelengths. At short wavelengths, it radically changes things. So at short wavelengths, which are very high frequencies, the size of the packet becomes really large. And as the sizes of the packets become larger and larger and larger, you become more and more unable to emit these single packets of energy. An electron, a hot, fast-moving, randomly moving electron, can't emit a packet of such a size. And so what this does is, what Planck's hypothesis does, is cut off. It stops the black body in classical theory radiating at short wavelengths, at high frequencies, because the packets are just too big for, I'm a single electron, right? And I've got to throw out a packet of energy, and that packet of energy is way bigger than the energy I have. I can't do it anymore. And so that cuts off the frequency. The frequency is no longer predicted to be infinite. It's predicted to be zero, in agreement with what is observed. Okay. I'm not going to go through all of this. It's like, this is my version of busy work. Calculate the energy in electron volts of photons with wavelength 5 centimeters, 500 nanometers, and 5 nanometers. So this is a different look at this question here. We want to calculate the energy of photons. Suddenly we've introduced the concept, the idea of a photon. That's a packet, a quanta of electromagnetic energy. So that's what a photon is, and we want to calculate the sizes of the packets for 5 centimeter wavelength electromagnetic radiation that corresponds to microwaves. We want to calculate it for 500 nanometer electromagnetic radiation, that's visible light, and we want to calculate it for 5 nanometer electromagnetic radiation. That's actually X-rays. So let's do one of these. I'll do it on the device I don't know the name of. Okay, so we want to calculate. I'm going to take the 5 centimeter microwaves. Let's do that one. And I want to calculate the photon energy for 5 centimeter microwaves. Now, the photon energy is related to the frequency of the 5 centimeter microwaves. So first, I want to calculate the frequency. So the first thing I'm going to do is calculate the frequency corresponding to the 5 centimeter microwaves. That's this equation here. So if you remember, for electromagnetic waves, if you take the product of the wavelength and the frequency, that's the speed of the wave, the speed of light. I've just rearranged lambda f equals c to be f equals c over lambda. All I got to do is fill in the numbers. 3 times 10 to the 8 meters per second is the speed of light. Nobody can forget that till we die. Lambda is 5 centimeters, 0.05 meters. And so all I got to do is divide 3 times 10 to the 8 by 0.05. I could almost do that in my head if I wasn't standing up here. And that's 6 times 10 to the 9 inverse seconds or hertz. So 6 billion hertz. 6 billion oscillations a second is that frequency of those microwaves. Now, it's easy to calculate the energy of a microwave photon corresponding to 5 centimeter wavelength microwaves. All I got to do is use Planck's hypothesis, concept, idea, that the electromagnetic waves come in little energy packets, and I've just got to multiply his value for the Planck's constant. I'm going to work in electron volts, not joules. I said this last time. I preached on forever about use electron volts, don't use joules. So I'm going to do that now. This is Planck's constant, energy times time. The dimensions in the units of electron volts and seconds. And then I've just got to multiply the 6 billion hertz, which is, just as a reminder, an inverse second. And so the seconds cancel out in the numerator and denominator. I'm just left with an energy, and it comes out to be 3.7 times 10 to the minus 5 eV. That's a tiny, tiny number of electron volts. And that's a tiny, tiny energy packet that's easy for electrons to, at typical temperatures to emit that size of packets. If we were to, I'm not going to do the other two cases. One was visible light. One was visible light where the wavelength was 100,000 times shorter than this microwaves. And the other one was X-rays, where the wavelength was 10 million times shorter than these microwaves. So if you were doing the other problem, you could do this, Or you could just say, well, look, let's take the X-rays. My X-rays wavelength is a factor 10 million times shorter. That means that their frequency is a factor of 10 million times larger, which means that the energy packet is 10 million times bigger. And so you discover that for X-rays, the energy packet is not 3.7 times 10 to the minus 5 eV, which is tiny, tiny, tiny compared to the sort of energy scales of atoms and molecules. The energy size of a packet becomes 370 electron volts, which is big compared to energy scales of electrons in atoms and molecules. And this is why that cuts off, unless you get something really, really, really hot, the radiation of blackbody radiation in the X-ray region. And so that solved the ultraviolet catastrophe. You've got to like the fact, or maybe I resent the fact, that Einstein, revolutionized space and time with a little bit of high school algebra. That seems unfair. Max Planck revolutionized, the quantum world, the microscopic world, with this isn't even high school algebra. This was like a kindergarten algebra. He was able to solve a massive scientific problem. That just seems we can't do that anymore. It just seems a little bit unfair. So I wanted to just voice my resentment. Okay, photoelectric effect. That's the second effect. This is the effect that took us one step further. So Planck's hypothesis really, although I introduced the word photon in discussing it, his hypothesis was really just that the energy in electromagnetic radiation comes in packets. He didn't use the word photon and didn't think about particles of light. The word photon and the particles of light came with Einstein and the photoelectric effect. So we're going to discuss the photoelectric effect. And I want to show the demo of it. I think I'm going to put the camera on. The photoelectric effect is a very interesting effect that photoelectric. What it means is that you shine light on typically a metal. So we're going to shine light on a metal. I'm going to shine light on the metal of this movable arm here. No, I'm going to shine the light on here. I've been an idiot. Photoelectric effect is shine light on a metal. And that metal can emit electrons. You can actually liberate the electrons from the metal. So we know right now that a metal is this, if we could peer inside, or if we got good imagination, we know that that metal is a vast ocean or sea of electrons. If we shine light on that metal, we can liberate some of those electrons from the metal. They boil off the metal, kind of like you put your saucepan on your stove and you heat up some water. You're going to boil off some of that water as steam. Here we're going to, with the photoelectric effect, boil off some electrons into the out of the volume of the metal into the surrounding space. Okay, sounds like science fiction, but it's not. Okay, so I'm going to show you that I'm liberating electrons from a metal. So this is the metal arm of this electroscope device that we talked about before. I'm going to charge it up. So as you know, we charge it up with cat's fur or whatever fur by rubbing it on plastic, right? This is ripping off electrons from one material onto the other material, and I'm going to apply some of that charge. I'm not going to apply some of that charge. Why not? Okay, I've got some charge on there. Now I'm going to try and get rid of it. I said, well, look, now I've filled this up with electrons. You can't see them, but I've added some electrons to them and to the metal parts of this electroscope. So I claim that if I shine light on it, so here's light. Obviously, we know that. Here's some light. I'm going to shine it on this piece here, and I'm going to try and boil off these electrons. If I boil them off, you'll see, as I lose electrons, you'll see this needle, which is being repelled from the solid arm because there's electrons on both the needle and the solid, rigid part. It's going to fall back down to the vertical. So let me try and do it. Now, you're thinking failed demonstration. But actually, this is not a failed demonstration. I can't do it with the visible light from this flashlight. It's not going to work. I got another extremely expensive special light. Now, you will be able to see it a little bit. It's an ultraviolet light. So you can see a little bit of the violet end of it. But this ultraviolet light is super bright in the ultraviolet region. Now I'm going to shine this light on it. Of course, to you, it looks less bright than the flashlight. But actually, it's more bright than the flashlight. I'm boiling off electrons. I'm not touching anything. I'm just boiling them off by shining this short wavelength, high-frequency light on the metal. And so that's the photoelectric effect. So the photoelectric effect, kind of like the black body radiation, has some certain features to it related to, the number of electrons that get emitted, like the brightness of the light, and the energies of the electrons, like the frequency or the color of the light. So we're going to explore, firstly, sort of the experimental features. And we'll discover, again, they could not be explained by classical theory. They had to be explained by the new quantum theory. And they were explained, as I say, by this idea, not just that the energy of electromagnetic radiation comes in packets, that the light itself comes in packets, particles that we call photons. All of this is due to Albert Einstein. Not only was he like the star of last week, but he's the star of today's class. Not only, we all know him because of relativity and E equals mc squared, but he also solved the photoelectric effect issue, catastrophe or problem or whatever it is. So what is it? Not a one-trick pony, I guess. He's done more than one trick. Okay, photoelectric effect. This slide is just to tell you the sort of things that, that you can measure with the photoelectric effect and the sort of results that you get. It's going to be really hard for me because the big conclusions have got cut off on the side here because of this stupid thing with whatever the projector is doing to me. So the photoelectric effect, as I say, what you do is you shine light on a metal and you liberate electrons from the metal. And this is an instrument to study the photoelectric effect upstairs here. So look, there's light being shone on the metal, like I shone light on a metal, and there are electrons here, I drew two of them, being liberated from the metal. What you can do, if you, okay, so that's fun, you could do it here. But what you would really be interested in, perhaps, is how many electrons are being liberated. Maybe even more interesting, it is more interesting, what's the energy? What's the energy of the electrons being emitted? So this is a clever idea to measure the energy of the electrons that are being emitted. So you shine light on the what's called the emitter here. So you're emitting electrons from this emitter, and you want to measure the energy of these electrons, the kinetic energy of these electrons. What you do is you put an electrical potential between the emitter and what we call this collector here. You make an electrical potential hill for the electrons to have to climb up from the emitter to the collector. So we're going to put a different potential, a potential difference between the emitter and the collector, such that electrons being ejected from the emitter to get to the collector, they're going to have to climb that hill. Now, to roll up a hill, you have to have sufficient energy, kinetic energy, energy of motion, to roll up the hill. So, if you make the hill shallow, a lot of electrons will be able to convert their kinetic energy into electrical potential energy, maybe to get up the hill. If you make the hill very high, a big potential difference between emitter and collector, then the electrons that can get to the top of the hill are going to have a lot more kinetic energy that they can convert into potential energy. So we're going to measure the kinetic energy of the electrons by asking them to climb a hill, an electrical potential hill, and that will determine the energy of the electrons. Specifically, it determines the maximum energy of the electrons. Because in reality, when you shine some light on a metal, electrons are boiled off with all sorts of energies. What we can measure by collecting the electrons on the collector is the maximum energy that those electrons have. And that's the interesting experimental quantity. When you liberate the electrons, like when I liberated the electrons, I want to know what is the maximum energy that they're liberated with. And how does that depend on the light that I'm shining on the metal? How does it depend on the brightness of the light? How does it depend on the color of the light? And this was the shocking result. So in classical theory, you'd think that the brighter the light, the greater the energy of the electrons. The more intense the light, the greater the energy of the electrons, because intensity is a measure of the energy in the light. But it turns out that that's not true. You can do the photoelectric effect with a very, very bright lamp, and you can do it with a not very, very bright lamp, and you don't change the energy of the electrons that get emitted. That's in a way bizarre. In one case, you're flooded with a bright lamp. You're flooding the metal with electromagnetic energy. The other case, the weak lamp, you've got very little electromagnetic energy on the metal. But in both cases, the electrons are emitted with the same maximum energy. That's very, very strange. What you do discover is what I discovered here, that the ability to liberate the electrons, and actually the maximum energy of the electrons, doesn't depend on the intensity of the light. It depends on the color, the wavelength, the frequency of the light. So what you saw me demonstrate was with visible light of relatively long wavelength, I couldn't liberate electrons. With ultraviolet light, a relatively short wavelength, I could liberate electrons. So the ability to liberate the electrons depends on the wavelength of the light, and also, we didn't measure it, but you can measure it. The maximum kinetic energy is determined by the color, the wavelength, the frequency of the light. It's not determined by the intensity of the light. And specifically, if you shorten the wavelength, that is increase the frequency, you increase the kinetic energy of the electrons. If you lengthen the wavelength, that is decrease the frequency, then you lower the maximum energy of the electrons. So that's the experimental observations. So the explanation of the photoelectric effect, then, Einstein's explanation of the photoelectric effect, is not only that does electromagnetic energy in electromagnetic radiation come in packets, but the light itself, the electromagnetic radiation, comes in packets or quanta we call particles, that are particles we call photons. And the way to imagine the shining of the light on the metal is not to imagine this smooth kind of electromagnetic waves sort of rolling across the beach of the metal and the metal being some continuous medium of charge. That's a very macroscopic classical picture of bathing the charge of the metal in electromagnetic waves. The right way to think about the photoelectric effect, rather, is to think of the incoming electromagnetic radiation as little bullets, little photon bullets carrying little packets of energy that are striking little targets in the metal, little electrons, individual electrons in the metal. And those photon bullets are hitting the electron targets, and some of those photon bullets knock electron targets out of the metal. And the point there is that the energy of the photon bullets depends on their frequency. That was Planck's hypothesis. If they're high frequency, they're going to be high energy bullets, and they're more likely to knock out an electron. And they can give that electron as much energy as those photons own. So if I'm a photon, right, here I come, you're a metal, you're an electron in a metal. I won't literally collide into you, but if you were, here comes the photon, I'm carrying some energy, I collide with you, I can give up to my kinetic energy, to you, and that could liberate you. And that's how we understand the photoelectric effect. Not by thinking of the smooth electromagnetic waves on that smooth distribution or sea of charge in the metal, by thinking of photon bullets striking the electron targets and those individual collisions. There's an equation, it's on this slide, I kind of buried it, that comes with that understanding. And it's this equation here. So let me just explain this little equation here. There's a few ingredients in it. HF. That's the energy that's carried by a photon of a particular frequency F. So this is Planck's hypothesis. Except now where it's not just the hypothesis that electromagnetic radiation comes in packets. It's that those packets correspond to individual particles we're calling photons. So this is the energy of a photon that we're shooting into the metal. This Ke, who's Ke? Ke is the kinetic energy. Ke is the kinetic energy of the electron that gets emitted. And so if we just were to look at this, ignore the phi for a moment, just look at this bit. This says that a photon brings in some energy, HF, that's the energy it carries. It strikes an electron, and that electron could be given as much energy as the photon owns. So it could be given an energy, kinetic energy, up to HF. And that's what this piece of the equation says. That the energy that gets transferred to the electron, the kinetic energy, is up to the size of the energy that's carried by the photon. It's that simple. The phi, that's just a little complication. So the electrons are not sitting there on the tabletop, and we're not shining photons on them on the tabletop and causing them to jump off the tabletop. The electrons are actually in a container. They're in the container we call the metal. So they're in the volume of the metal. To liberate them from the metal, to liberate them from that container, actually costs some energy. So to just pull an electron out of a metal, right, if we did it with tweezers, right, that would cost us some energy to get it out of the metal into the surrounding, into empty space. That amount of energy, that's called a work function, is given the symbol phi. So actually, in the individual collision, the photon could give all its energy to the electron, but the electron would have to use some of it up to get out of the metal for us to see it. And so we subtract off that amount of energy, the work function of the metal, we subtract off the phi. So that's this piece here. And what I've described is how we understand the photoelectric effect through the picture of packets of electromagnetic radiation, photons, particles of electromagnetic radiation, individually colliding with electrons inside the metal. And that explains the features of electromagnetic radiation. It explains why the radiation, the kinetic energy of the electrons doesn't depend on the intensity of the light, but it depends on the frequency of the wavelength or the color of the light. Okay. Well, this is just a cartoon. Just to give me a breather. So in the classical picture of the photoelectric effect, sort of the macroscopic picture, the electromagnetic radiation is just waves of electromagnetic radiation that impinge on a metal, which is a sea of charge. To understand the effect, we have to understand that in those electromagnetic waves are little particles of light, photons of light. That's what these little things are here, these little worms. And they're striking inside the metal, inside that sea of charge, individual electrons. And here, a photon liberates this electron. Here, another photon liberates this electron, and so on and so forth. It's just like, in a way, like weird billiard ball collisions from, I don't know, first class of Physics 211. But it's at a microscopic level, and not with billiard balls. It's with photons, and it's with electrons. Okay, quiz question. So in this quiz question, you're asked to think about photoelectric effect, and you're asked to pick which statement is correct down here. So there's a couple of statements about does the maximum kinetic energy of the electrons, I just say maximum energy, but does the maximum kinetic energy of the electrons depend on the intensity of the light? Or does the maximum energy depend on the wavelength of the light? And if it does depend on the intensity, or if it does depend on the wavelength, does increasing either the wavelength or the intensity increase or decrease the kinetic energy of the electron? So I'll give you another minute to think about that. I am feeling a lot of pressure to get one more example in, so I won't give you much time. Okay, so to give the electron more energy, to give the electron more kinetic energy, you've got to have a higher energy photon. The photon's got to be carrying more energy. That's sort of an obvious thing about billiard ball collisions, and it's an obvious thing about photon-electron collisions. To have a photon with more energy, it has to have a higher frequency, has to have a corresponding shorter wavelength. So the correct answer is that to create higher energy electrons in the photoelectric effect, you need to decrease the wavelength. You need the shorter wavelength of the electromagnetic radiation. Okay. Here's a question on the photoelectric effect. I'll at least do the first half of it. It says zinc's work function is 4.3 electron volts. So all metals have different work functions. We're asked to figure what's called the cutoff frequency and wavelength. Now, the cutoff frequency of wavelength is what we saw in my demonstration. The light from the flashlight had a frequency that was too low to eject the electrons, had a wavelength that was too long. The ultraviolet light, that had a frequency that was high enough to emit the electrons. It was a wavelength that was short enough to emit the electrons. So there's a cutoff. There's a cutoff frequency, there's a cutoff wavelength that determines whether you simply can or cannot emit the electrons. I'll show you how to get the cutoff frequency. It's from this equation for the maximum kinetic energy. Remember, this equation for the maximum kinetic energy is that the maximum kinetic energy is the energy carried by the photon less the work function. Well, the cutoff point is when the kinetic energy is 0. If you have a smaller energy photon, then you simply can't emit the electrons. If you have a larger energy photon, then you can emit the photons and they carry off whatever energy is left after subtracting off the work function. So if we set this to 0, the frequency becomes the cutoff frequency. So the cutoff frequency is simply equal to, if I rearrange this equation now, by taking phi from one side to the other side and divide it by Planck's constant, the cutoff frequency is simply the work function divided by Planck's constant. In our case for zinc, this is 4.3 eV, and the Planck's constant is 4.1 times 10 to the minus 15 eV seconds. If I divide one by the other, if I divide one number by the other, I get the frequency. It's 1 times 10 to the 15 hertz, roughly. And if I wanted the cutoff wavelength, remember we've got to get below the cutoff wavelength, shorter than the cutoff wavelength, to actually liberate the electrons. All I need to do is use the relationship between wavelength and frequency. So remember, lambda f equals c, and so if we want lambda, it's just c divided by f. In this case, it's the cutoff frequency that we divide by. And if I plug in these two numbers, I've got 3 times 10 to the 8 meters per second divided by the frequency. It was 1 times 10 to the 15 hertz.